All right, thanks, Tom. Okay, so first of all, I want to clear up a couple of things that were confusing in the problem session. It's first of all, the one that caused the most confusion was the positive definiteness. And what I had in mind was something terribly simple. It was just that, so let me flip back to that. It was simply that if you have the matrix 1, minus 1, 1, 1, then of course if you have real vectors, then this thing is, well, if you it turns out to be just a squared plus b squared, and this is obviously greater than or equal to 0. What I had in mind when I wrote the example a few years ago is that if A and B are both imaginary, for example, and this is strictly negative, that's all I meant. It wasn't anything profound. If, on the other hand, you take the next step by saying that, well, what about if we reinterpret this as being A bar, B bar, 1, 1, minus 1, 1, AB. Well, then what you get is A squared plus B squared plus, let me see, it's, well, I didn't work it out. It's A bar B minus B bar A. And so then, if A bar B has an imaginary part, then this is twice the imaginary part of A bar B. Consequently, the whole thing is complex, so it's not non-negative, and so you've demonstrated what's needed. You don't need to show that it's actually negative. Now, you can't make it actually negative because of these terms. Okay, so that's that. Is other? Yes. You're either hungry or puzzled.
So actually, my question has to do with your book. I have checked Amazon and I've checked the bookstore. Nobody has a 2014 edition.
Oh, I'm sorry, you're saying the bookstore doesn't have it?
No, actually, I checked it also. It says there's 2013, but then there's below it says reprinted with 2014.
Yeah. That's what it is. Yeah,
it's 20. I just came over. So it does say 2014 on it?
It's inside the front cover.
There's only one edition. It's reprinted. Reprinted with corrections 2014. That's the one you want. And I talked with Amazon yesterday, and I don't think I got anywhere. So maybe I'll call them tomorrow.
I'll go by after class.
The other possibility is calling or sending email to Cambridge, which has offices in the United States, and they will probably sell it to you for, well, I don't know, less than the bookstore, let us say, but yes.
I got the ISBN number from the bookstore, and then I could get the reprinted edition from Amazon, and so that worked out. If anybody's trying to.
Oh, you got one from Amazon, and
yeah,
it
yes,
was.
And it's
has
reprinted in 2014
with corrections. With
reprinted with corrections.
Yeah. Okay, good.
Okay.
All right, but
I
the ISBN number,
because the problem with Amazon is they have this warehouse that's the size of New Mexico, and when they grab a book out, one might be 13, one might be 14. I don't know. But Amazon is very good about sending things back. If you get the wrong one, you can send it back and give you a free refund. And you can have them send it again. Okay. The other thing that was puzzling to some people was the example 1.13, this is again from the problem session, but it's a reasonable example. We had a basis vector v1 was 1, 0, B2 was 0, 1, and we decided that the linear transformation would be represented by the matrix 0, 0, 1, 0. Okay, great. Then I said, if you have a different basis, and it's 1 over root 2, well, that's weird. Oh, I see, all right. B1 plus B2, but these are sort of abstract vectors, but they are represented this way, so B1 prime is 1 over root 2, this plus that, so that just gives you that. And B2 prime then is 1 over root 2, 1 minus 1. So then the question is, what's the matrix that takes you from one to the other? Well, in the notation of the example, it's U inverse that takes you there. And then you can see that what you're going to need is a 1 over root 2. And you want something that takes you from, the U inverse takes you from the B's to the B primes. So what you want is something that takes, you want something that takes 1, 0 into 1, 1 with a root 2. So you divide by root 2 and you put 1s there. You don't need to know what these are. Then you want to take the other one, you want to take 0, 1 into 1, 1. No, not 1, 1. 1 minus 1. Well, you just put 1 minus 1 there. So that's U inverse. 1, 1, 1 minus 1. And now you notice that this thing is, it's unitary, it's real, it's orthogonal. So the inverse is just a transpose. So U is the transpose, but U equals U inverse. So that, I hope, tells us everything we need to know about that example. All right. Any further questions? For people who've come in late, homework is problems 1 through 4, due Thursday, 27 all. And if you guys find that too much, complain on Tuesday.
Is the website up?
Excuse me?
Is the website up?
It's getting there, but it's not up yet. Tom Hess and I were working on it for a good fraction of the afternoon. It's mostly there, but it's not quite there. However, the link to the errata still exists. It still works. It goes to the other.
I worked on it very hard.
All right, now, I want to talk about something that's very important, that those of you who've ever had a course in linear algebra, you've heard about this, but maybe it wasn't emphasized, or maybe it was, I don't know. It's inner products. And inner products are things that are really important, and they allow you to define norms and distances in a vector space. And moreover, well, at least if the vector space has an inner product. And they're the main thing in quantum mechanics. The amplitude for one state to become another is always an inner product. And the probability of that happening is the absolute value square of that inner product. So the reason why I emphasize inner products is that they're absolutely essential in quantum mechanics. It's also true in special and general relativity that distances in space-time are inner products. Okay, so let me just, I'm going to do it in a semi-mathematical way. and which will distinguish several different kinds of inner products. Maybe it'd be good to rotate the camera a few degrees. So, first of all, positive definite. A positive definite inner product. Okay. So the idea is that it associates a number, and the mathematicians like to write it this way. I'll show you later that Dirac introduced a much better way of writing things. In fact, the number of improvements to physics and mathematics that Dirac introduced, it's absolutely astounding. Okay, so in other words, an inner product takes you from two vectors, f and g, into, these are vectors then, into this, which is a number. And in many cases, it's a complex number. And now, if it's a positive definite, this is called the inner product, and if it's positive definite, then FG is GF complex conjugate. In other words, you reverse the vectors, you get it like that. By the way, you don't have to take extraordinary notes in my class because I'm basically following the book very closely. So you can sort of just pay attention and ask questions and then read the book at home. You may say, why am I following the book so closely? Well, Dirac was I'm not comparing myself with Dirac. Totally different order of human being. But Dirac wrote a famous book on quantum mechanics. It was an excellent book. And when he was teaching in Cambridge, he would actually just stand at the podium and read the book. And he wouldn't even write on the blackboard. And some students said to him, Professor Dirac, we can read the book at home. Why don't you just read the book to us? And Dirac said that when he wrote the book, he expressed his thoughts as clearly as possible, as clearly as he could. And if he were to deviate from the book, it would be less clear. Now, I don't know, I don't go that far, but the advantage of following the book closely is you don't have to take notes. That's one advantage. And the other is, I did try to make it as clear as possible. I don't know, occasionally. I will say things which will, I hope, be a little bit different. Because I'm not just following the book the way Dirac followed his book. All right. Next property of this inner product. Suppose Z and W are complex numbers. G and H are vectors. So F is a vector, G is a vector, H is a vector in some vector space. The inner product of F with ZG plus WH is Z times the inner product of F with G plus W times the inner product of F with H. And this is basically, this is saying that this property is called linearity. Linearity in the second member, not the first. This property is called hermeticity. Yes?
What changes if you make the linearity in the first term?
I'll get that. That's actually a homework problem. I'll get to it in a moment.
It's the problem.
There's a third condition. I'll get to, but you do get a candy. Good catch. Okay, the third property is related to that example over there, namely that FF, the inner product of a vector with itself, is non-negative, and if FF is 0, then F is equal to 0, and of course the inverse. If F is equal to 0, FF is 0. So this is the positive definiteness condition for a positive definite inner product. So once again, this hermeticity And by the way, this in quantum mechanics, you will often be required to use that property, that Fg is Gf star. That's the key to understanding a zillion things in quantum mechanics. Then you have linearity on the second member, and then the positivity, namely that the inner product of the vector with itself is always non-negative, and if it's zero if and only if the vector is the zero vector. So this is the really strict, strong, this is your gold standard for an inner product. I mean, this is the one that, frankly, in most mathematical contexts, and in particular in mathematical physics, most often you're dealing with this kind, but not always. Let me say then that if you take the first two rules, you can show that the inner product is antilinear in the first member. That is to say, that ZG plus WH, that inner product, with F, is Z star G with F plus W star H with F. Okay. So you can prove that, and that's one of the homework problems. So that's, okay. All right, so this is the gold standard positive definite inner product. Then there are two or three others. So let me go to the next one. The next one is the Schwarz inner product. The Schwarz inner product. Okay, in this case, we certainly have the first two rules, hermeticity and linearity, but we're going to weaken the positivity condition. And instead, the Schwarz condition is that the inner product of a vector with itself is always non-negative. So that's the condition for a Schwarz inner product. So it's just the first part of the gold standard for positivity or non-negativity. But there's something you can prove from it, namely that this condition, non-negativity, that this thing implies this rule, that if FF is 0, then GF is 0 for all G in the vector space. Okay, so always we were talking about some sort of a vector space. So in other words, the Schwarz inner product satisfies the first two rules, hermeticity, linearity in the second member. Then it also satisfies this rule of non-negativity. And those three rules in turn imply that if a vector has a zero Schwarz inner product with itself, then that vector is orthogonal to every vector in the vector space. So it's a little different from the other one. It's weaker, certainly. So it's basically, it's almost positive definite.
Silver standard.
Excuse me?
If that's the gold standard, would the Schwarz inner product be the silver standard?
Yeah, okay, sure, here.
Oh, no, that wasn't. Oh.
No, that's all right.
More thinking out loud.
Should I be a W star?
All right, hold on. Yeah.
Should that be a W star over on the left top?
Yeah, that is W star.
Oh, I can't see it from here. Okay.
Z star, GF plus W star,
Oh, yeah,
HF.
on the left-hand side.
Where?
Z star. G
This is
plus
just W.
W. So why?
That's W, that's W star, this is Z, this is Z star.
I'm not sure.
Anything else? Okay, so the next, of course, is the inner product that you run into when you do special or general relativity. And
When you have something like this.
these are indefinite inner products. So this is an indefinite inner product. So what do? We say, first, it satisfies the first two rules. And by the way, once you satisfy the first two, you automatically satisfy this one. So that's true of Schwarz, for example, also the indefinite ones. But the fourth rule for an indefinite inner product is this. If Fg is 0 for all F in V, that implies that G is 0. So in other words, if there's a vector that's orthogonal to every vector in the space, then it has to be the 0 vector. So it's not, it doesn't have anything to do with positivity, because in fact you can have vectors that have a negative inner product. But the case of a negative inner product, or an indefinite inner product, this, as far as I know, I can only think that it's the one that occurs in special or general relativity. And I'll give that as an example in a moment. But first, let's finish the story here. If we have either a positive definite one or a Schwarz one, the inner product of a vector with itself is always going to be non-negative. And that allows us to define a norm. So the norm, all right, let's get rid of indefinite here. That's the end of indefinite. So now the norm for the gold or the silver standard, to use his notation, is you just say the norm of a vector is simply the square root of the inner product of the vector with itself, because that's always non-negative. Right. And that allows you to define a distance. The distance between two vectors is the norm of their difference. And so then you have a metric space. Your vector space is a metric space. So if you have a vector space with a gold or silver in a product, then that gives you what's called a metric space. All right, so now the obvious examples are Euclidean space, where the vectors are, U would be some vector with a bunch of real numbers, R1, R2, Rn, and V would be, well, R1 prime, R2 prime, Rn prime, R just meaning real, and then you would say U comma V was just R1 prime plus R2 prime plus Rn prime. So that's the inner product in Euclidean space. This is the one that you know about from first year physics, freshman physics, and probably high school physics if you went to a fancy high school. Anyway, the inner product of U with itself, you just remove the primes, and then it is just effectively a sum, Ri squared, I equals 1 to n, and so obviously since these are real, this is non-negative. In fact, this is also a gold standard, because if the inner product is 0, the only way it can be 0 is if all the r's are 0, but that's what we call the 0 vector. And when this thing vanishes, we say the vectors are orthogonal. So that's Euclidean. Then there's complex Euclidean space. And there, the difference, I can just use these same equations. We just have u and v, but now the u with the v would be, we put a bar on the r's, complex conjugate. And so now it would be the absolute value of these guys. And so bingo, that's also gold standard. So this is gold standard, all right. Okay, so that's that. Now, complex matrices. This is a little more subtle. Suppose you have two complex matrices, and suppose they form a vector space. Well, that means they have to have the same dimensions, because we need to be able to add them together. They don't need to be square, but they need to be 3 by 5, all of them 3 by 5, or all of them 67 by 42, whatever. But they have to be all the same size. Then you can define an inner product this way, A with B, and it's the trace. Remember the trace that I mentioned. This is not H bar. It looks like H bar, but it's not H bar. And what we do is we use the adjoint of A. Remember we talked about that last time, times B. And so what is that? That's then a sum. And let me actually follow the book carefully here. Suppose these are n by L matrices. Then this will be I equals 1 to n, j equals 1 to L, and it will be A dagger ji bij. And of course, this dagger means that we've got a sum ij n L. This thing is now A complex conjugate ij b ij. Now you see how clever this is, because if the matrix is the same, the B is the same as the matrix A, then this is just a big sum of Aij complex conjugate Aij, or in other words, a sum on Ij of the absolute value of Aij squared. So this is gold standard. And in fact, in quantum mechanics, this is the two norms that basically you use in quantum mechanics are this complex vector. It's complex Euclidean vector space, or you generalize it to a Euclidean space with infinitely many components, or even continuously infinitely many components, depending on what the situation is. But it's basically a natural generalization of the complex Euclidean space. And then when you're dealing with matrices, you do this norm. And this is called, by the way, the Hilbert-Schmidt norm. Okay. And obviously this can vanish only if every one of the matrix elements of A vanishes. So that's why it's gold standard. All right, so let me take a swig of this. Costco coffee. Yeah.
So, if we just look at the first line, it said AB is the trace of, like, if we try to do that using the trace formula, it seems like you just get the diagonal elements, or am I missing?
You get the diagonal elements of the product.
Okay. And that's why you get some of all of the elements?
Yeah. Here, I'm throwing with my left hand, so watch out. Okay, now I'm going to go through some definitions that are somewhat mathematical. Okay, and I'm doing this mainly because these are definitions that people toss around when they teach courses in quantum mechanics, and in my experience, never explain. There's a great deal of mathematics that people refer to in quantum mechanics and quantum field theory courses. That's just, it's not in the, people aren't taught it, and so it makes things difficult. All right, so let me just mention, if you have a positive definite inner product, then people call it, so the gold standard, so you have a gold inner product on some vector space V, okay. Then V is an inner product, space. So it is, and as I said, it's also a metric space. And one can also call it a pre-Hilbert space. So those are three different terms that are used. Okay, now let me say something else. This is just a definition that you may have heard about in college. A Cauchy sequence. Okay, so Fn is a Cauchy sequence of vectors. If for every epsilon greater than 0, there is some integer n of epsilon such that Fn minus Fm, the norm of that is less than epsilon when n and m are both bigger than n of epsilon. So the idea is you have a Cauchy sequence if you can shrink the norm of all the vectors, of the difference of any two vectors, lower than any positive, given fixed positive number, as long as you go far enough out in the sequence. That's called the Cauchy sequence. Okay, next is the definition of convergence. Fn converges to F, and it's essentially the same thing. If for every epsilon greater than 0, there's again some n of epsilon such that Fn minus F is less than epsilon, or n greater than n of epsilon, capital N. Maybe I should have used, probably should have used subscript m instead of n. But anyway, so this is the standard definition of convergence. A sequence of vectors converges to some vector if you can shrink, get the norm arbitrarily small if you go out far enough in the sequence. So the next thing is a definition. If you've got an inner product space, is complete if every Cauchy sequence Fn converges to an F in the vector space. So the idea of is you have something that looks like convergence, being the Cauchy property, and then you have real convergence. If every Cauchy sequence converges to a vector that's in the vector space, then the vector space is complete. And you can see the idea of completeness, namely that when you have a convergent sequence and you have a Cauchy sequence, so things are sort of converging, but there's the possibility the vector is in the space, the sequence converges to a vector to be in the space or not in the space. And if it's in the space always, then it's a complete vector space. You might say, well, let me give you a quick example. Suppose you have the integral the unit interval, but without the endpoints. Now, this isn't a vector space because you add these guys up and you get outside. Okay, I know that. All right. But you can you can show it also fails the completeness test, because suppose you have a bunch of x's. You can have a bunch of in fact you can say x